For the given circuit, I will find Thevenin's voltage for terminal AB and Norton's current for terminal AB. So Thevenin's voltage means the open circuit voltage VAB, which is VOC here. And in order to do that, what I will do, I will apply node voltage method. So this is, if this is the reference node, I can see there is one node here, and the voltage of that node will essentially be Vx, because this is a there's a voltage rise of Vx here, which is the control voltage of this current voltage control current source. So now I will write KCL for this node, the voltage of which is Vx. So Vx minus 30 over 12 is this outgoing current. The outgoing current downwards will be Vx over 60, and finally 2Vx is the other outgoing current, and this one is open circuit anyway, AB. So like that. So what I will do now, I will multiply both sides by 12, so 60, so it will become 5Vx here minus 150 plus this one will be just Vx, and this one will be here multiplied by 60, so 120 Vx is equal to 0. So that will be 126 Vx is equal to 150. So Vx is 1.1905 volts. Now we can see here from the circuit, this Vx is actually VOC, because there is no other drop here. So Vx is Thevenin, which is Vx is 1.1905. so this is the Thevenin's voltage. For the same circuit, if I want to find Thevenin's current, Norton's equivalent current, so that will be short circuit here now, and I want to find the short circuit current here. So in order to do that, what I will do, I will convert this voltage source and the series resistance into a current source and a parallel resistance. That will, if I do that, it will be much easier. So this there, and then I have this one, and this is my short circuit. So this is 2Vx here, this is 60 volts, which is Vx, this is 12 ohms, which is the series resistance of the voltage source. It is becoming now the parallel resistance with the current source, and the value of the current here will be, the voltage source value was 30 and the resistance was 12, so it will be 30 over 12, so 2.5 amps. So this is the current. Now when I look at this circuit, the short circuit current will, this is a voltage controlled current source, and with this arrangement, this resistance will be short circuited, this resistance will also be short circuited. So Vx will essentially become 0. There won't be any Vx, because the whole current 2.5 amps will go in this direction. So this current source 2Vx will also become 0, since the voltage drop Vx is 0, which is the drop across 60 ohms resistance. There is no current through 60 ohms resistance. So from direct observation, we can just write I short circuit, which is I Norton, will become 2.5 amps. 2.5 amps. So that will be the Norton's equivalent current. So these two I have found. Now what I will do, I want to find out the equivalent resistance as seen from terminal AB. So in order to do that, since I am drawing the original circuit again, so in order to do that, since there is a dependent source, instead of making sources, we cannot make the dependent source inactive. So what I will do, I will make this source inactive. So this will be short circuited. This is 12 ohms, 60 ohms, sorry, and this is 2Vx, and this is the drop Vx, and I will apply a current source here of 1 amps, and I will see what is the voltage drop here, and I will divide the voltage drop by the value of 1 amps, which is just the value of the voltage source, of course. That will be my Thevenin resistance as seen from here. So I will just apply a current to find the equivalent, the resistance seen from this terminal. So when I do that, I will again apply Norton node voltage method here. So V voltage here is again Vx, the voltage of this node, and this is the reference node. So I will write the outgoing currents. So one outgoing current will be this one, which is Vx over 12, then Vx over 60 will be this current, and then 2 Vx is coming downwards anyway, so plus 2 Vx, and this current is going inwards current to inwards to the node, so that will be 1 here, 0. So I will multiply both sides by 60. So this is the KCL for that node, for this particular node, this one. So when I multiply by 60, it is 5 Vx plus Vx plus 120 Vx minus 60, so that's 0. So it's becoming, so 126 Vx is equal to 60. So Vx will become 60 over 126, which is 0.476 volts. So this is the voltage Vx. So R Thevenin or R Norton, that is the resistance seen from there, is Vx over the value of the current source, which is 1. So that will be 476 ohms, or we can write 476 milliohms. So 0.476 ohms, or I multiply by 1000 and write it in terms of with the unit of milliohms. So that's the resistance seen, the Thevenin's or Norton's resistance for seen from terminal AB, which is this terminal.